Greetings. Today we're going to learn about iterated integrals. But first we're going to do a Calc 2 warm-up. Now this is something you've already learned in Calc 2. You should be able to do this. We have a solid and its basis in the xy plane bounded by some curves. So let's sketch that. So here, bounded by the graph y equals x cubed. Let me draw y equals x cubed. And also the y-axis, well, I've already drawn the y-axis, the line y equals 8. So that means I have this region that's bounded by those three curves. And I'm going to try to sketch this in 3 dimensions. Z going above as usual, x here, y there, and I need to sketch this region, probably something like this, and then y equals to 8. This is 8 right there, and then we have that the cross-section perpendicular to the x-axis, that's right here, those are squares. If I draw one right here, I should get a square. So that's a square. And the cross-sectional area of that square, we are denoting a of x, is equal to, well, the side length squared. What is the side length? The side length is the distance from 8 to the curve x cubed. So that length is 8 minus x cubed. So that quantity squared, that's the cross-sectional area. And then part D is to find the volume of the solid using an integral. So volume equals integral of from something to something of this cross-sectional area. 8 minus x cubed quantity squared dx. And x goes from 0 to something. What is that something? We haven't solved for that yet. That's here. That's 2. That's 2 cubed is 8. So that's the intersection between y equals 8 and y equals x cubed. So that's 2. Similarly, right here, that's 2. And here it's 2. So this is an integral. Surely you know how to do it. I don't really want to calculate it. I did it earlier. It's, I think, 576 over 7. Whatever, it's some number. Right. So now let's move on to the next one. So we're doing the same thing again. Suppose this solid has a rectangular base, so that's a little easier. Base, the xy plane. X is between 1 and 3. And y is between 0 and pi over 2. Why did it cut off? That's really awkward. Okay, 0 and pi over 2. Oh, that's a rectangle. So let me now try to draw in 3 dimensions. The region is x equals to 1, x equals to 3, y equals to pi over 2. That's this region down there. And then we have cross sections perpendicular to x-axis. So let me draw a thin little slice. That cross section is bounded above by the graph of the function something. Okay? I don't really know what that function looks like, but let me just pretend, let's say the graph of that function is like this. I mean, it's a cosine of something, right? This is probably the wrong drawing, but whatever. So that's the top. The top is f of xy equals x squared plus cosine y. That's the top. So then this cross-sectional area, a of x, is equal, well, what is that? So we're given an x value, like maybe it's 2, so I'm interested in a of 2. When it's 2, to get the area under the curve, I would, what would I do? I would integrate this thing, x squared plus cosine y, integrate with respect to y, because y is changing, and I'm getting the area under the curve there. Remember, x is just a number, because x might be 2, for example. That's just 4 plus cosine y, and we integrate it, we get something. Y goes from 0 all the way to pi over 2. And so that's the integral. So, and that's an area. And then we have the volume is equal to, like before, integral of the cross-sectional area, a of x dx, and x moves from 1 to 3. What's different now is that this function that we're integrating, like the one above, here we're integrating a function of x, here we also integrate a function of x, but that function of x is given as an integral. Well, you've seen integrals that give functions before, but if you substitute this in there, you're going to get an integral inside an integral. So that's a little scary, but that's what we're doing. That's what we're learning today. Now, putting an integral inside another integral. So let's try to calculate this one. But first, let me pretend I'm trying to calculate a of 2. If I'm trying to, well, maybe I'll try a of 2. Calculate a of 2.3. So I'm interested in knowing, maybe this is 2.3 right there. I'm interested in cross-section area when x is 2.3. What is that? According to this formula, it's 0 to pi over 2 integrate 2.3 squared plus cosine y dy. What is that? Well, I know how to integrate this. What's the integral of cosine y? I think that's plus sine y. What is the integral of 2.3 squared? It's 2.3 squared times y. If I take the derivative, then I get back 2.3 squared. Take the derivative there. Evaluate it from 0 to pi over 2. And so that gives me 2.3 squared times pi over 2. Sine of pi over 2, what is sine of pi over 2? It's something. I'm blanking right now. It's probably 1. Yeah. And then sine of 0 is 0. Okay. So now let me try to calculate a of x. It's the same thing. Here, this is equal to x squared y plus sine y, evaluated from 0 to pi over 2. If I take the derivative of sine y, I get cosine y. If I take the derivative of x squared y, I get x squared, because x is just a number. X might be 2.3, it might be 1.7, and so forth. And we're treating x as a constant. So in some sense, we're taking partial derivatives here. No one says this, but you're trying to take a partial integral. Okay? But I've never heard anyone say that. And when we substitute this in, we get pi over 2x squared plus 1. And notice that this formula is the same as that one, where we evaluate x at 2.3. And now we have this quantity, we can put that in here. So this volume is equal to integral from 1 to 3 of pi over 2x squared plus 1 quantity. Integrate that, and that's some number. I did it earlier. It's equal to 2 plus 13 pi over 2. The back of the worksheet starts by explaining what we just did. I wrote it because I wanted you to have instant feedback when you're working on the worksheet. So I just talked about this, so I'll skip that. So we have an iterated integral because we're integrating twice. We'll try this again. We're calculating this iterated integral. You see that this could have come up from a calculation involving solids in 3 dimensions. But now let's just treat this abstractly. We're trying to evaluate this. We're going to evaluate the inner integral first. So that's integral 1 to e to the y, integrate with respect to dx with respect to x. So the question is, what is an antiderivative of y over x when we're integrating or taking the derivative with respect to x? Well, the antiderivative of x is log absolute value of x. Y is just a constant right now, so I'll write it in front. Y is just a constant. We're treating y as a constant. And we'll evaluate this from 1 to e to the y, and that's the x value. So then if we write that in, we get y of log of the absolute value of e to the y minus y times log of 1. So that's y squared. Log of e to the y is y. This log of 1 is 0. And then I already told you the answer. Again, because I put it in because you're working on a worksheet without me around. So I made it so that you could continue and check your work. So all we need to do is calculate that one. And you know this one. This is y cubed over 3. Evaluate from 0 to 1. That's 1 over 3. Okay. The thing I wanted to teach you is you can write all of this out in a single line. So we were calculating integral 0 to 1, integral from 1 to e to the y of y over x dx dy. And that's equal to 0 to 1. Integral of y over x, that's y log of x, evaluated from 1 to e to the y. That's this inner integral right there. We still have a dy outside. And then usually I have to do one step and simplify this. So plug in e to the y there, I get y squared. And then if plug in 1, get 0. That's this. And then I can do this. And then get a final answer. So in the future, what I would like you to do is simply do this. Don't break it out and calculate the inner integral first and then go integrate it. Do it all in one step. Now let's try this one again. Not again, sorry. Try this one. Here, I will rewrite this first. Recall that e to the 3x plus 4y is e to the 3x times e to the 4y dx dy. So because we're integrating with respect to x, y is a constant. If y is a constant, then e to the 4y is a constant. if e to the 4y is a constant, you know this integral, you can pull the constant outside. So then we can pull that outside. E to the 4y integral 0, 1, e to the 3x dx dy, where, let me parenthesize so you can see clearly. Right here I have an iterated integral. Right here I have integral, and I've pulled the e to the 4y outside. So ignore the integral 1 to 2 of dy. That's just on the outside. If you had seen this integral in Calc 1 or Calc 2, and then you have a constant here, like e to the 4 pi, let's say, you would have pulled it out e to the 4 pi in front. So you get to do that. The nice thing about doing this is, let's think about this. If we integrate e to the 3x, don't do it. I know you know how to integrate it, but don't do it. And then we evaluate from 0 to 1. This is a number, right? This is a definite integral, and it's a number. So in other words, it's a constant. So now we have an integral with respect to y of e to the 4y times a constant. We can pull the constant out in front. So that's equal to, I'll pull the constant out in front. That's the constant in front times the integral 1 to 2 e to the 4y dy. Once we pull that out, we can integrate them separately. So this is just a trick I wanted to show you based on what you already know. So we didn't have to do these things in the iterated sense. We can pull them out. So then this is equal to e to the 3x over 3, evaluated from 0 to 1, times e to the 4y over 4, evaluated from 1 to 2. So that's e cubed minus 1 over 3 times e8 minus e4 over 4. So that's my answer. All right, that's it for today. Bye.